So what Lewis structures tell us, they show us how valence electrons are arranged in a molecule. So we primarily focus on the Lewis structures of covalent substances. The idea here is that we want to figure out how we can look at the stability of a compound in relationship to the noble gas electron configuration. So again, covalent compounds, that's the key here. We're working with covalent compounds, and we are going to use something called the need available shared method on structures that are not exceptions. So just like some of the other topics we've talked about in chemistry, there's exceptions here. We're not going to focus on too many exceptions. There's one main exception that we're going to focus on. Not all of them. There are a lot. So you remember from last unit where we were talking about the octet rule, how most elements like to have a full octet because they like to have 8 electrons. There's also something called the duet rule. The duet rule applies for hydrogen and helium. Hydrogen and helium only can hold 2 electrons in their valence shell. So their goal in order to achieve maximum stability is to have 2 electrons. So they follow the duet rule. And because helium we don't really bond things with because it's extremely stable, we really just focus on it with hydrogen. So with ionic bonds, which we've talked about primarily up to this point, ionic bonds, we transfer electrons and have those charges. Covalent compounds, we share. So because of this sharing, there's a lot of implications from it. And one of the things are covalent bonds. So there's actually 3 different types of covalent bonds: single, double, and triple. So I have examples here of all of them. A single covalent bond is a covalent bond where 2 atoms share 1 pair of electrons. Whenever we're talking about electrons, we often talk about them in pairs. So think of when you talk about your shoes in pairs. Whenever we talk about a pair of electrons, it's really referring to as 2 electrons makes, in this case, a single bond. So 1 pair gives us a single bond. We represent that as a single line. A double covalent bond is a covalent bond in which 2 atoms share 2 pairs of electrons. So rather than 1 pair, we now have 2 pairs. So 1 pair is 2 electrons, 2 pairs is 4 electrons. And 3 pairs of electrons in a triple bond would be 6 electrons. You can actually have a quadruple bond. They're kind of rare. We don't really worry about them in this course, but you can have it. It would just be 4 pairs, and it would have 4 lines. Again, they're pretty rare. So we're going to practice our needed available shared method for drawing some more simple Lewis structures before we get into the more complex ones. So the first one here, we have H2, which is hydrogen gas. For every problem, we're going to write N, A, and S, which stands for needed, available, and shared electrons. What we're trying to figure out is how many bonds are needed in order for this molecule to be stable. So needed electrons, this is what is needed in order to achieve maximum stability. So we have 2 hydrogens. Each hydrogen follows the duet rule, meaning it would want to have 2 electrons in each to achieve maximum stability. So 2 electrons in each, 2 atoms, means that we need 4 electrons. However, each hydrogen only has 1 electron. So that means we have 2 electrons available to us. So what we end up doing is we subtract this, and we'll see that we have 2 shared electrons. Now what I always do when I see the shared electrons is I always take that and divide it by 2, because then that will tell me how many bonds I need. So for this molecule, I need 1 bond. This is a more straightforward one. We have hydrogens. We're just going to connect them with a line. That's it. You probably could have drawn this Lewis structure without doing any of this needed available shared stuff, but we're practicing the idea here. Okay, so what we then would do is count up to make sure all of our atoms have the appropriate quantities. So each hydrogen in this case has 2 electrons, meaning they have their maximum stability. Next up, we have F2. Fluorine is what we have here. We're going to do the same thing. So we have needed, available, shared. Each fluorine, in order to achieve maximum stability, would follow the octet rule, having 8 electrons. We have 2 atoms, so that means we need a total of 16 electrons. We have fluorine is in group 17 on the periodic table, meaning it has 7 valence electrons. So in total, it has available 14 electrons. We're always referring to valence electrons in this case, just to clarify. So we'll subtract this and we'll end up with 2 again. So we're going to divide that by 2, which will tell us we need 1 bond. So what we're going to do, we're going to take our fluorines and bond them together with 1 line. That 1 line is representing those shared electrons. However, when we check to make sure that fluorine has its maximum stability, right now each fluorine only has 2 electrons. That's not fulfilling the octet rule. If you remember back, we have a total of 14. We use 2 of the electrons here, so we have 12 electrons left. What we're going to do with those electrons is we're going to put them into our molecule as lone pairs. You're going to equally distribute them. So I'm going to draw in as dots in pairs, and each fluorine is going to get 3 pairs. So if I add up my electrons now, I have 2, 4, 6, 8, 10, 12, 14, which is exactly the same as the number I have. In these problems, you can't add electrons, you can't remove electrons. You can only have the electrons that are there. Now, again, just to reiterate, when you're drawing these are referred to as dot diagrams. You want to make sure you have your electrons paired together. That's an important step. Sometimes I'll show you an example. So let's say we had oxygen. How many valence electrons does oxygen have normally? 6. So sometimes what this is, students will just take their 6 electrons and kind of equally space them throughout. We don't want to do that. That's not good. We want to have, you draw 1 on each side and then pair them normally. So when we're doing this NAS method, we're kind of just filling in these already lone pairs of electrons. They're already there. We don't have to worry about them. So just to kind of keep that in mind, we draw them in pairs when we can, and when we don't, we draw them as singles. Okay. So we're going to do one a little bit more complicated, and that is with HF, or hydrofluoric acid, if you remember back to acid naming. So hydrogen would need to fulfill the duet rule, which would have 2 electrons. Fluorine would have the octet rule, which would have 8. So we have a total of 10 needed electrons here. We have 7 from the fluorine because it's in group 17 on the periodic table, and 1 from the hydrogen, giving us a total of 8 electrons. So we have 2 that we need to share, which will result in 1 bond. I know all of our examples we had 1 bond. That's usually not the case. It's just because these are a little bit more simple examples. So we're going to have H bonded with an F. Hydrogen now has fulfilled its duet rule. It has 2 valence electrons. Fluorine now also has 2, but that's not fulfilling its octet rule. So we have to add the 6 remaining electrons, which we're going to put on the remaining available sides. The big thing with also the paired electrons, this bond represents electrons. You don't want to put your lone pairs in between your atom and your bond. That doesn't work.